Chinese is normally written as an unbroken string of characters, which doesn't have spaces in it. And you can see an example here. And the second line here shows what the sentence looks like when we put spaces between the words. This video is about implementing an algorithm which automatically detects word boundaries in Chinese text. It automatically puts spaces between words. And this problem seems a bit esoteric and also kind of impossible to me because I don't know any Chinese. But that's actually why I'm doing this project in the first place. The fact that I can write a program that solves the problem without my having any knowledge of Chinese tells me something important about some kinds of AI, like deep learning. So for deep learning problems, what I mean by that is problems that involve neural networks, you don't have to know how to solve the problem yourself because we're not writing a traditional AI program in which you have to write out explicit steps for solving the problem. Instead, you show the neural network thousands of examples and the answers that you want the network to output for that data. In this case, I'm actually not using a neural network. I'm implementing a decision tree, but the same thing holds for decision trees. I'm feeding the decision tree thousands of examples, thousands of data points, and then I'm telling the decision tree what the answers for those data points are. In this case, the data consists of thousands of sentences of unbroken strings of Chinese characters, and the answers I'm showing the decision tree are how these sentences should be broken up into words. The algorithm that I'm implementing, which will automatically find word boundaries in Chinese text, is based on this paper from 2008. And the main idea of the paper is to split the lines of unbroken Chinese text into foregrams. When I say foregrams, I mean we're looking at groups of 4 Chinese characters at a time. So let's look at an English example. Let's say we have an unbroken stream of English characters that look like this, and the string has the words "May the Force be" in it. I didn't make it a complete sentence because that doesn't matter. It doesn't have to be a complete sentence. So from this string, we create a list of all the foregrams in it, and you can see this list of foregrams here. I add this caret symbol, which is this weird symbol here. I add it to the beginning of the string, and I add the $ symbol at the end because it helps with our algorithm. What we do is we create a sliding window that looks at 4 characters at a time and assigns a label to those 4 characters. The label says whether a space should appear between the second and third characters in the foregram. So let's go through an example. Here's the first foregram that we look at, and we ask the question, should a space appear between M and A, the second and third characters? And in this case, the answer is no, because we don't want to split up this word may. We don't want to put a space there. So the answer is no, and so that foregram, this foregram that we're looking at in this little window, we look at 4 characters at a time, this foregram gets a label of 0. Then we move the sliding window 1 space to the right, and we're looking now at this foregram, which consists of the letters M, A, Y, T. And we ask the same question, should a space occur between the second and third characters? And again, the answer is no here. So the answer is no, and this foregram also gets a label of 0. We move the sliding window over to the right, and in this case, we do want to put a space between the second and third characters because a space should appear between the word may and the. So this gets assigned a label of 1. So we do this for all the foregrams in our corpus of Chinese text. So here's what our training data looks like so far. Each foregram has a label. So there's the foregram, and that's its label. But we're not going to feed the foregrams directly into the decision tree. For one thing, you can't do that. You can't feed characters into a neural network or a decision tree. Neural networks and decision trees can only take numbers as input, not characters or words. So let's look at a different example here. It's still English characters that we're dealing with here. Let's say the foregram is A, B, C, D. This will get a label of 0, let's say, because no space should occur between A, B, and C, D. We're going to represent this foregram with a 5-dimensional feature vector of unigrams and bigrams that look like this. So we're splitting this foregram into these pieces that you see here, and it has a label of 0. This list of 5 things is just another way of representing this ABCD foregram. We're kind of helping out the decision tree here by turning ABCD into this list of 5 things, because we're really being explicit here. We're showing what all the different pieces of the foregram are to help the decision tree learn. We're saying to the decision tree, okay, this is what our foregram looks like. It starts with the bigram AB and then has the bigram BC and the bigram CD in it. And we're also telling the decision tree that when you see AB and CD, don't put a space between them. That's what the label equals 0 is saying here. And we're also saying that the 2 most important single characters in this foregram are the second and the third characters B and C here. And the label is telling us that no space should go between them. Okay, so we've transformed the foregram ABCD into a more explicit list of 3 bigrams and 2 unigrams, which you see here. Like I said before, we can't feed characters into our decision tree. We can only feed it numbers. So we have to represent the list of 5 character type things with numbers somehow. And so how do we do this in a meaningful way? In the example, we're dealing with English characters, letters of the alphabet. So we can represent the unigrams, the single characters B and C, by their positions in the alphabet. So the letter B is represented by the number 2, and the letter C will be represented by the number 3, because those are their positions in the alphabet. So how about the bigrams, the 2 character items in the list, like A, B, B, C, and C, D? How do we represent them with numbers? We use this grid, this kind of matrix or grid, which has the letters of the alphabet here and the letters here. So there are 26 times 26, which equals 626 numbers to represent all the possible bigrams. And we can assign each bigram a unique integer by what its position is in this matrix or grid that I'm showing here. So for instance, the bigram AB will have position 2 in this matrix, because that's where it shows up in the grid. And the bigram BC, it's on the second row here and in the third column, and so it has position 29 on the matrix, because there are 26 entries here, and then 26, 27, 28, 29. It occupies space 29 in the grid. Similarly, CD will have the position 56 in the grid. So these are the integers, the numbers that we can assign to these bigrams and unigrams that are in this 5-dimensional feature vector that I've been talking about. The last step is that we're not going to actually feed this list of 5 integers in the decision tree as they appear here. Instead, I'm going to create a big one-hot vector version of this list of 5 numbers. The bigram numbers will be represented with 1s in this left part of the array, and the unigram numbers will be represented with 1s on the right part of the vector. For instance, AB will get a 1 in position 2 in this array, and BC will get a 1 in position 29 of this array, and CD gets a 1 assigned in the position 56 of the array, and then zeros appear everywhere else. So that's a one-hot vector that represents the bigrams in our list of 5 pieces of the ABCD string. And then similarly, in this portion of the one-hot vector, which is where our unigram information goes, we put a 1 in position 2 here to represent the B, and we put a 1 in position 3 here to represent the C, and zeros go everywhere else. So this is what our final one-hot vector will look like. That's the information that we're feeding into the decision tree. So notice that this part of the vector will have 676 entries in them. There will be 3 1s in here, and all the rest of the entries will be zeros. And this part of the vector will have 26 numbers in it. There will be 2 1s, and the rest will all be zeros. Here's just a summary of what I've been talking about in the last few slides. Our example involved the foregram ABCD, and we assign it a label of 0 because we're saying no space should occur between the second and third characters. We create this 5-dimensional feature vector, which is the parts of the string, the unigram and bigram parts of the string. We assign numbers to those unigrams and bigrams, as we saw, by either the position of the unigrams in the alphabet or the position of the bigrams in that big grid that I showed you. And then finally, we turn this list of 5 numbers into a long one-hot vector that looks like this. So this example was for the English characters, for a foregram which was ABCD. But remember that the problem that we're working on here is about Chinese text. So the number of Chinese characters is much larger than the number of characters in English. There are only 26 characters in the English alphabet, whereas Chinese has thousands. For instance, I searched a corpus of Chinese text and found 4,660 unique Chinese characters in it, and there are even more than that. Those were the number of unique Chinese characters that I found in our corpus. And so the grid, or the matrix that we'll be using to map bigrams to those numbers, it won't just be 26 times 26 entries in it. There will be 4,660 times 4,660 entries in it. So that's what the grid or the matrix will look like for the Chinese characters, and it'll have these dimensions. That's a very big one-hot vector that we're dealing with here. The one-hot vector that we end up for just a single foregram will consist of almost 22 million zeros and ones. Most of them will be zeros. Because there are so many zeros, it's mostly zeros in here, just a few ones, we're going to use Python's SciPy function that's called CSR matrix. And we're going to use that to represent these very big one-hot vectors that are mostly empty. We don't want to take so much space up in our memory, and CSR matrix allows us to represent these one-hot vectors in a very efficient way where we don't have to actually store 22 million zeros and ones for a single 4-gram. My code creates a whole bunch of Chinese 4-grams and assigns labels to them. The training data for the decision tree consists of about 1 million labeled 4-grams, and the development set contains about 120,000, and the test set has 17,000 labeled examples in it. So let's take a look at the code. Up above in this Jupyter notebook, I create all the Chinese 4-grams and assign labels to them. And actually, it takes the code a long time to create that data because we're dividing the Chinese corpus into 4-grams and then labeling that. So it took hours to do that kind of processing. And down here is where I implement an XGBoost decision tree classifier. And I train it on the 4-gram data for 40 epochs, I think. Yeah, 40 epochs. I could have trained it for longer because after 40 epochs, you can see that the loss is still decreasing here. But I stopped it there because of time constraints. And so when I evaluated the classifier on unseen test data, I got the following results. Accuracy was 85%, precision was 95%, recall 80%, and it had an F1 score of 86.7. In this notebook, I compare how the computer formats some Chinese text with how a human does it. The lines prefaced with an H here means that this is how humans segmented the text into words, and the lines prefaced with a C, so like this one, is how the computer did it. So in this example, the computer got everything right. It inserted the spaces between characters in the same way that a human would. Here it does everything correctly until, so this is the way the human did it, this is the way the computer did it. It does everything correctly until here. It doesn't put a space here where it should have, because that's the way a human did it. And then I think it makes another mistake. Yeah, it puts a space here where it should not have. There are 33 places where the computer has to decide whether or not to insert a space in the characters. So 31 out of 33 of those decisions were correct, but it screwed up in 2 places. So 31 out of 33 is about 94%, and that corresponds with the precision score I showed a few slides ago. The precision of the classifier on the test set was 94.7%. Thanks for watching.